we could have said, okay, well, then it's not fitting into what we're working on. Let's move on. Let's put it to the side. It's not our business, right? But instead, we really picked our curiosity and we decided, no, we'll throw everything in the kitchen sink at it. We're going to figure out what this is.
This is the Discovery Files podcast from the U.S. National Science Foundation. I'm Nate Potker. Truly groundbreaking research in healthcare is occurring all across the country, transforming how we approach tissue repair, disease treatment, and organ replacement. Regenerative medicine focuses on repairing, replacing, or regenerating human cells, tissues, or organs to restore normal function. We're joined by Maksim Plikus, a professor of developmental and cell biology at University of California, Irvine, where his lab studies the mechanisms of cell regeneration. Professor Plikus, thank you so much for joining me today.
Thank you for having me on your show.
So I think we need to start with a little definition as we move into this topic. And for people that don't know, what is regenerative medicine?
So regenerative medicine, at least in my interpretation, is an aspect of medicine that relies on innate ability of our tissues to repair themselves. And these innate abilities are then harnessed for the benefit of producing, for instance, new replacement tissues that either diseased or tissues lost to injury could be substituted.
Thinking about approaching regrowing human tissues, how do you do that?
So I think, obviously many people are thinking about it. Many people are working really actively on it. I think it's one of the really fast evolving fields with huge potential. So I think a lot of hopes are that it will work the way, we scientists promise it will. I think everything is quite, depends on context, right? So I think first question one would want to ask is, what is the problem that needs to be fixed? And actually, depending on a problem, regenerative medicine solution would actually differ quite a bit. We can obviously go into an example. So if, for example, there is a catastrophic loss of skin, such as to a burn, then what one would want to do is to, completely replace the lost skin. And then we already right now are able to produce skin substitutes that burn victims could be grafted with. But when you look at what we're able to do right now, the skin substitutes, and you compare it to our actual skin, you quickly realize it's really simplistic. It lacks a lot of components that normal skin has that makes it what it is. So I think the best, outcome of use of skin substitutes is a tissue that looks a lot more like scar and a lot less like normal skin. So we still have a long road to go. So we need to build much more intricate substitutes that, for example, contain hair follicles so new hair can grow, or sweat glands so that skin substitute could later sweat and help us in thermoregulation. So we understand that our abilities to build super complex tissues that match in complexity those that we normally have is still quite limited. And then, of course, there are other applications for regenerative medicine where, I think a really classic example is type 1 diabetes, where patients lack insulin producing beta cells in the pancreas. So clearly, if something is lacking, you can just put it back. So why don't we make many more insulin producing beta cells and transplant it to, diabetes patients? Shouldn't that work? And in principle, it sounds like it should. But the nature of the disease is autoimmune. So your own immune system will go after transplanted beta cells and kill them off again and again and again. So then it turns out that regenerative medicine solution for diabetes is a little bit more than just transplanting cells or tissues. It's also protecting them from your own immune system. Right. So, and I think one could really go into a list of examples where all these details matter so much for the success of the therapy, once it's ready.
Thinking about your research here that we're going to be talking about a bit, what is lipocartilage and where do you find it in the body?
This is obviously in its name, lipocartilage. It's some kind of cartilage with some kind of lipids, right? And that's
Right.
exactly, this name really encapsulates what it is. It's a lipid-filled cartilage tissue. So it's really fatty skeletal tissue, if you want me to put it that way. Where it's found, that's a good question. It's not found everywhere. So not every single cartilage in our body is full of fat. It's in our facial structures and neck structures. So earlobes, cartilage in our earlobes, cartilage in the tip of our nose, also cartilages that make up our larynx. So that's where you find lipocartilages. And yeah, so I think that would be kind of like a short answer. And of course, they're so different from a typical cartilages, right? So the typical cartilages do not contain lipid in their cells. They just contain a lot of extracellular matrix. So this is, proteinaceous substance outside of the tissue. So many questions then arise. Why is the lipid in the cartilages in our ear and nose and larynx? What is it doing there? Is there benefit to it? What's so special about it, lipids? So this list of questions can really go on.
What research were you doing, or what question were you trying to answer when you guys found this?
It was quite simple. We identified somewhat on an accident. Okay. So, and we were a little bit puzzled by it because, okay, so the real context is the following. We were looking at pieces of skin that should have adipocytes. So adipocytes, for your audience, are obviously uh, fat-filled cells, but very different, right? The ones that make up our fat tissues. They look in the very certain way under the microscope. So you can envision them. They look like a really beautiful pearl that is iridescent. One light shines on it, like it just like really has this like iridescent look to it, very pretty and very big. So then we were looking at the small pieces of tissue coming from a mouse ear, and we're looking at the adipocytes, and we were finding them. So yeah, there was all this iridescent cells there. But once we start stating them for markers, we kind of realize, wait a second, only a small portion of the cells labels with markers of an adipocytes. And the larger portion, even though they look exactly like adipocytes, they don't label. So first thought was like, we must be looking at rather very unusual, maybe different type of an adipocyte. And then as we start digging a little bit more and more, trying to define this adipocytes, we came to this realization that, wait a second, these are not adipocytes at all. These are actually cartilage cells that masquerade themselves as an adipocytes. They look like adipocytes, but molecularly, they're completely different. And at that point, when it sort of kind of hit us, we realized, oh, we are dealing with a distinct skeletal tissue, lipid-filled cartilage. And at that point, we really put into high gear trying to learn more.
Was that an exciting finding for you guys? Like, why did this
Yeah,
go overlooked for so long?
it was kind of super exciting. Um, you could imagine it's pretty rare in 2025 to stumble upon a cell that nobody else have seen before described, right? So you immediately start to question yourself, like, wait a second, I must just not know something very obvious. And if you ask experts in cartilage, they'll say like, oh, come on, of course like you're missing something. You should go back to your medical textbooks and read them, right? So we did that. So we just like couldn't believe that nobody else saw them before. And lo and behold, people did. And the first person who actually described these cells in the ear cartilage of a rat was this really well-known scientist and contemporary of Charles Darwin. His name is Francis Leidig. So he worked in, what is now Germany, in middle 19th century. So in 1854, he first described it in his book. And, I don't remember like the exact word to word translation of, his description in German. He drew it, by the way. So we knew he was looking at the same thing. But basically it said, when you're looking at the cells under the microscope, you think you're looking at adipocytes, fat cells. But you know that this cannot be because what we put under the microscope was cartilage. So thus, we must be dealing with fat-filled cartilages. Case closed, moved on. And then he moved on to other things. And the rest of his book is just like a wild, exploration of everything that he could potentially find and put under the microscope. So, contemporary Charles Darwin already found it. And then for almost like 100 years, nobody seemed to have looked back and realized that there's this cartilage that has all this lipid in it. And then in 1970s, there was a few papers, descriptive papers, when electron microscopes became actually fairly affordable. And people start sticking all kinds of stuff under electron microscopes now. And sure enough, somebody put ear, and sure enough, they realized that, oh, there's this very beautiful lipid vacuoles in the cartilage. Let's describe it. And so they did. And, people working at that time were also quite diligent because they went back and they dug out Francis Leidig's original description. They gave a credit to it. So, and then in like early 90s, all of a sudden, nobody's talking about it again, right? So we essentially were like a third wave of rediscovery. But now, to our advantage, we have all these molecular tools and methods available. So then we, other than just like describing how they look, we start studying the molecular biology, the physiology. And as we were doing it, we realized that there's so many unique aspects about this tissue and about the cells, we still know very little, but therefore we're actually super excited because of what's possible, what's lying ahead.
So thinking about those possibilities a little bit, does the lipocartilage cell lend itself towards regenerative medicine potential usage?
I would argue that yes. There are many instances where cartilages of our face and neck need to be replaced because, for example, they poorly develop due to birth defects. Birth defects of earlobes actually really common. Trauma of the ears, face, and neck is common. There are certain forms of cancer that could locally invade into like structures of the nose and neck. And to save patients' life, that needs to be all cut out. And, surgeon would have to remove large portions of this cartilage. And then what you're having at that point is big defect in the face or neck. So this all calls for replacement strategies. So, and of course, there's category of, elective plastic surgeries where it might be beneficial to produce new cartilage because, it's like nasal augmentation, things like that. So then the question is like, okay, well, where do you source this type of cartilage? Turns out cartilage is one of these tissues that, if you're talking about autologous cartilage, you can cut pieces of the rib cartilage and then shade it. And that's exactly how it's done. Then you can kind of shade it and then place it, for example, into the tip of the nose or the ear. But by just like touching your rib, it's not as soft, right? You can touch your ear and see how just pliable and elastic and bouncy it feels, and then touch the rib, right? And it's totally different. So biomechanics of tissues are like not the same. So you're not really doing one-to-one replacement. And on top of it, cutting out cartilage of the rib is on its own very invasive. So it's not a joke. Try to do something like this. And then any substitutes, people will also think, okay, well, can we go to like synthetic materials? Can we replace cartilage with, say, silicone implants? And yes, you can put a silicone implant that is shaped, for example, like an ear. But silicone is a foreign body. And our body knows that this is a foreign body. And it will try really, really hard to reject it. And it will like encapsulate it or form a capsule around it. So longevity of the synthetic implants is actually not very high. They're also just not ideal. So there needs to be new solution that is, I think one solution that we envision can regenerate a lot of face and neck specific cartilage, which is lipocartilage, from, let's just say, pluripotent stem cells in large numbers, and then shape these cells into tissues that match exactly what we're aiming to produce, like, a shape of an ear. And that would be, if this works, really a regenerative medicine solution for these guys.
And would make a lot of difference for a lot of people that are suffering from those kind of issues.
Would agree with that.
I would like to pull out a little bit and look at the kind of regenerative medicine field in general. Like, I think last year I heard a story about being able to regrow teeth a little bit. What kind of things can actively be regrown at this point in time?
I teach a class to my undergraduates called Advances in Regenerative Medicine. And every year I feel like I have to go back and change something, because over a year span of time, things have advanced dramatically. Oftentimes, there is just new research that came out a month before I have to start teaching in class that would completely change the lecture, because what I taught last year is all of a sudden out of date.
Right.
And that really means that this is such a fast evolving field. Almost every month, there's some new discovery, some new advances in regenerative medicine that have been reported. So it's really exciting. And at the same time, like, it's really hard to stay on top of this, to be current. But, a lot of understanding has now exists of what can we do at this point in time, and what else we need to learn to do to really translate all this very promising stem cell based approaches into real therapies that could help people. And I think that turns out to be a multifaceted problem. There's a lot of things that we still need to learn. I can go into some of them, but I think there will be just so many so many questions that we still need to get answers to. I think the bottom line at this point in time, scientists have learned, for the most part, how to use really potent stem cells, such as pluripotent stem cells, and how to direct them to make cells that we intend. Okay, so for example, can we make cartilage cells? Can we make chondrocytes? Can we make skin cells, keratinocytes, and on, right? I think the answer to those questions is like, yes, we've learned. So there are essentially molecular recipes. When we culture cells, we can direct them toward these outcomes that we desire. At the end of it, though, what we have is really a suspension of cells. Okay. But our tissues are, for the most part, not suspension. They're highly intricate, very large, and morphologically really well organized. So then the next challenge is that, how do we put the cells into this microarchitecture of tissues? How do we generate tissues that are not just tiny microscopic, we need a magnifying glass to see them? How do we make them big? Because we are fairly large, organisms. So how do we make something that's like 10 by 10 centimeters? And that turns out these are the challenges: the scaling of things, the micro patterning of things. It's still often, we don't really know how to go about it. But a lot of research is in this area. So,
thinking about research, I want to ask you about how NSF support has impacted your career so far.
NSF support was absolutely fundamentally essential for us to be able, to think outside of the box and feel like, we can, support our efforts. Because at the point in time when I mentioned in my earlier answer, when we were looking at adipocyte, because, the project that we were working on was on adipocyte.
Right.
And at the point in time when we realized that, this iridescent pearl-looking cells are actually chondrocytes, there's some kind of interesting cartilage that nobody knows anything about. We could have said, okay, well, then it's not fitting into what we're working on. Let's move on. Let's put it to the side. It's not our business, right? But instead, we really piqued our curiosity, and we decided, no, we'll throw everything in the kitchen sink at it. We're going to figure out what this is. So it was in many ways like just this ability to do research in a completely new direction.
Fantastic. So for my last question today, I want to ask you, circling back to the lipocartilage, and I want to ask you about what's next. What are you excited to learn about it in the next couple of years?
Many things, but amongst those so many things is biomechanics. I think that's really interesting, because skeletal tissues is about biomechanics. right? But our bones, our cartilages, they provide our bodies with, support. And then when we, meaning scientists, typically think about biomechanics of cartilages, almost always we think about molecular properties of the extracellular matrix, like things such as collagen. How this bendable molecules endow cartilage with its properties, like such as elasticity, stiffness.
Right.
But now in lipocartilage, there's very little of this extracellular matrix. And instead, there are very large cells filled with lipid droplets. So then a question that we really, really want to get the answer to is, what is the role of intracellular lipid droplets in tissue biomechanics? We already have clues suggesting that they play an essential role. And then so that really suggests that the lipocartilage biomechanics, they're a composite material made by nature. It's the intracellular lipid droplets working together with extracellular matrix proteins, producing this composite tissue whose biomechanical properties derive at this like synergy point. So trying to learn that is that what we really want to do next.
Special thanks to Maksim Plikus. For the Discovery Files, I'm Nate Potker. Please subscribe wherever you get podcasts, and if you like our program, share with a friend and consider leaving a review. Discover how the U.S. National Science Foundation is advancing research at nsf.gov.